So let's take a look then at how we solve some of these problems in our packet. All right, so you were to finish up page 3 and 4 this past evening. So what I would like for you to do is to go to page 5. Page 5 has some review problems like the ones that you've been doing, but it also has this tricky problem number 9. So I'm on page 5, and I would like for you to take a look at problem number 9 on page 5. Can you guys see that okay in here? I can make it a bit bigger. I lied, I can't make it bigger. Sorry. Let me turn this. Maybe this will do something. I can make it bigger. Cool. So hopefully you guys can see that problem now. So we are given grams of C3H6, and we're given grams of NO. Now 3 moles of H2O plus 12 moles of NO plus 5 moles of C3H6 yields 15 moles of carbon monoxide plus 12 moles of ammonia. So there we have our balanced equation. We're given these two amounts. So this could be like our Kool-Aid packets, this could be our sugar, or whatever, right? So we want to first figure out, it says how many grams of carbon monoxide can be produced with these two amounts. So we start off with both amounts. And we're going to see how much this amount of propane can make. And we're going to see how this amount of nitrogen monoxide can make. So we're going to do 2 stoichiometry problems here. Remember, the first step is to get to moles. Every 1 mole of C3H6, 3 times 12.01 plus 6.06.
It's 42.09.
Actually, I'll go with what they say. 42.08 is fine. I'll go with the ones at the top. That way nobody's concerned. And for NO is 30.01. So now we have moles of C3H6 and moles of NO. We don't want this. We want to figure out grams of carbon monoxide for both of these. So every 5 moles of C3H6 is 15 moles of CO. And every 12 moles of NO is 15 moles of CO. We don't want moles of CO, we want grams of CO. Every 1 mole of CO is 28.01. Right, the last step in this is both the same because we've already switched to moles of CO. And then all this does is change it to grams of CO. So now it's a game where we basically just have to sit there and calculate it out. 1.44 divided by 42.08 times 15 divided by 5 times 28.01.
The answer is about
2.8755 equals 2.88 grams of CO. 2.5 divided by 30.01 times 15 divided by 12 times 28.01. 2.5 divided by 30.01 times 15 divided by 12 times 28.01.
It's about 2.9167.
And that's 2.92 grams of CO. So, $1 million question. Which of these amounts can we actually make? This much NO will make 2.92 grams of CO, and this much C3H6 will make 2.88 grams of CO. If we mix these two together, how much can we really make? If we have enough sugar to make 3 pitchers of Kool-Aid, and we have enough Kool-Aid packets to make 10 pitchers of Kool-Aid, how much can we really make? Three, right? We only have enough sugar to make 3. So again, if we have enough propane to make 2.88 grams of carbon monoxide, but we have enough nitrogen monoxide to make 2.92 grams of carbon monoxide, how much carbon monoxide can we truly make? It's 2 separate amounts. This amount of propane can make 2.88 grams of carbon monoxide. This amount of nitrogen monoxide can make 2.98 grams of carbon monoxide. How much can we truly make?
2.88 grams of carbon monoxide.
We can only make 2.88 grams of carbon monoxide. Even though we have enough nitrogen monoxide to make more than that, we don't have enough propane. So after you figure out both amounts that can be made, you pick the one that is less. Hey, put your mask on. If you're talking on the phone, you need to leave. I can't, because I'm trying to talk here too. 2.88 grams of carbon monoxide is the only amount that we can make because we only have enough propane to do so. This is in excess right here. This is our limiting reagent. That's the restricting factor. This is in excess. What's in excess at your house right now? Probably salt. You probably have enough salt for a while, right? Because you don't need a lot of salt and stuff. Maybe you've got enough flour and sugar for a while. These are things a lot of time we buy in bulk so that they're in excess because we're always using them. Let's try one more. This is on the last page. This is on page 8. So page 8, we have 4 moles of aluminum plus 3 moles of oxygen yields 2 moles of aluminum oxide. So number 10 here, number 10 says we have a reacting system starting out with 4 grams of aluminum and 3 grams of oxygen. How many grams of aluminum oxide can actually be produced? So we have a problem here. We have 4 grams of aluminum and 3 grams of oxygen. We want to solve for each of these to get grams of aluminum oxide. So oh, wrong place. We need to put that on bottom so that it will cancel out. I know it. I got writing happy. Now, since we're going from grams to something, the only thing we can do is go from grams to moles. Every 1 mole of aluminum is, from the periodic table, 26.98 grams. And every 1 mole of oxygen is 16 on the periodic table, but there are 2 here. So that is a total of 32.00 grams. So now we have moles of oxygen and moles of aluminum. We want to get something of aluminum oxide. So now is our only time. We want to change from moles of aluminum and moles of oxygen to moles of aluminum oxide. So every 4 moles of aluminum makes 2 moles of aluminum oxide. And every 3 moles of oxygen makes 2 moles of aluminum oxide. We don't want moles, unfortunately, we want grams. So again, we're going to use that mole train or whatever, that bridge, and go from every 1 mole of aluminum oxide, every 1 mole of aluminum oxide is how many grams of aluminum oxide? Let's look it up. 26.98 times 2 plus 16 times 3.
The answer is 101.96.
101.96 grams is 1 mole of aluminum oxide. That number came from the periodic table. These numbers came from the balanced equation. These numbers came from the periodic table. The numbers come from the periodic table when we're trying to go from grams to moles or from moles to grams. Four divided by 26.98 times 2 divided by 4 times 101.96.
The answer is about 7.5581.
3 divided by 32 times 2 divided by 3 times 101.96.
It's 6.3725.
So we have 7.56. Yeah, question? And from going from grams to moles. Yep. These are from the periodic table. These are from the balanced equation. Nope. So if we take a look, with 4 grams of aluminum, we can make 7.56 grams of aluminum oxide. With 3 grams of oxygen, we can make 6.37 grams of aluminum oxide. If we put both of these together to react, which of these amounts can we truly make? So if we put both of these into react in the system, which of these amounts will actually be truly made? 6.37. Why? Because it is the amount that is the what? Smaller. We said in class that it would be the 6.37 because it is the amount that is smaller. Why is that smaller amount the amount we can make? Because we only have enough O2 to make this much. Even though we have enough aluminum to make this much, the O2 is the limiting factor. So O2 is the limiting reagent. This is in excess. It's just like our Kool-Aid thing that you just kept saying the same word over for. Hey, quit touching everything. Questions here. This would be known as the theoretical amount that you could make. A student in the laboratory made 2.55 grams. He should have been able to make 6.37 grams theoretically. This is his experimental. That's what he did in the laboratory. Theoretically, the math says he should have been able to make this amount. I think the student messed up. Because whenever we find out the percent yield that he makes, 2.55 divided by 6.37 times 100,
The answer is about 40.0313.
he only got 40% of his yield, what he should have been able to make. Experimental over theoretical. So this is the experimental that the student did over the theoretical that we got with math. And we get 40.03. But here is the deal. Sometimes experiments don't go out the way they plan. You call that error. But sometimes the chemistry itself only allows for so much to be produced. Because the process, it loses things in other processes. Something doesn't form correctly. They used to make insulin from, you guys know what insulin is? This is a drug that people that diabetes need to inject. They used to make this by using horse and cow, basically hormones from horses and cows to make this insulin. It wasn't a very good % yield, and it took a lot of animals to do this. And animals require a lot of food and water. An Indiana native, an African-American scientist named Percy Julian. Percy Julian found a way to make insulin using plants. And Percy Julian found that he could have a much better % yield, and you could grow a lot more plants on the same land mass that it would take to grow animals. Plants grow very quickly and do not take as much food, nutrients, fertilizer, and stuff like that. They do take water, but still not as much water as a cow would need each day. So there we go. You are to complete page 5 and 6. 5 and 6. I will put the answers up for this in just a few minutes so that you can track your work. If you do come across a problem and you have a question, the Zoom will still be open. After, I do have to close it before though. So keep that in mind. I have to close it so I can have this recorded version to put on the daily agenda. But if you do have questions, I'll open it within about 2 minutes of closing it. If you have questions right now, go ahead and ask. Otherwise, you guys are more than welcome to get out of the Zoom and go work on these problems. And have a great weekend, Friday the 13th.
Mr. Jackson,
Yeah,
on page 4, can you go over question E?
I can. Page 4.
Yeah.
Question E. So formula units is a fancy way to say products. I'm sorry, particles. Ew. Formula units is an easy way to say particles. So right there, that may actually be enough to help you with it. But let's go ahead and go through it real quick. It says how many formula units are produced when 35 grams of K2S reacts with excess amount of FeCl3. So we've got more than enough, right? This is excess, so we have more than enough K2S. I'm sorry, we have more than enough iron 3 chloride, so we don't even have to worry about that. So 35.0 grams of K2S. 39.70 plus 32.06.
The answer is 71.76.
I'm sorry, it's 39.10 plus 32.06.
It's 71.16.
So every 71.16 grams. Ah, dang it. I messed up again. 39.10 times 2 plus 32.06.
It's 110.26.
There we go. Is that what you got for that sub? Is that what you got for the molar mass? 110.
Yeah.
Okay, cool. So now we have moles of K2S. So we have to have this equation balanced. Every 3 CLs, we need, I'm sorry, every 2 FEs, we need 2 FEs. That's 6 CLs. 6 Ks, that's 3 Ks. So that's 3 S's. So every 3 moles of K2S makes 6 moles of KCl. So every 3 moles of K2S makes 6 moles of KCl. Now it actually asks for how many formula units we need. And formula units is again just like particles. So every 1 mole of KCl, you know the number of particles in 1 mole?
6.02 times
That's right.
10 to
6.02 times 10 to the 23rd formula units. And then we're going to put that into the calculator. 35 divided by 110.26 times 6 divided by 3 times, and remember how to put 6.02 in there, 6.02 times 10 to the 23rd. That E23 thing, right?
Mm-hmm.
So we get 3.82 times 10 to the 23rd. Formula units.
Wait, how come we didn't do anything with the FeCl3?
So remember earlier when we talked about limiting, this is saying it's in excess. So it doesn't matter. This is like water. We have more than enough of this FeCl3. It's basically a way to prep you for talking about limiting reagents and excess reagents. So
Oh, so is that just there to throw me off or something?
it's there to make you think what that means. It's
Oh,
there
okay.
to,
So it doesn't have like
it doesn't
any
affect the
purpose.
problem. It's basically just trying to prepare you for whenever you give you 2 amounts of something, and then you've got to figure out what's in excess. So it's a
Okay.
preparation for you.
All right. Thank you.
You're welcome.
Mr. Jackson,
Yeah.
if I came in contact with Jeremy like on
Hold on one second.
Tuesday,
Hold on one second. Hold on one second. Let me stop this Zoom real quick.